Good morning, everyone. I'm Sherry Ansakrias, Assistant Professor in the Department of EC at Rajagiri School of Engineering and Technology. Today, I will be discussing on the topic Principles of Sensing and Actuation. This comes under the Module 2 of the subject MEMS for S7 EC students. The contents of this presentation are as follows. We will discuss on the various principles behind sensing and actuation in MEMS devices such as electrostatic sensing and actuation, thermal sensing and actuation, piezoelectric sensing and actuation, as well as magnetic sensing and actuation. The reference textbooks are Foundation of MEMS by Chang Liu and MEMS and Microsystem Design and Manufacture by Tyran. Now we will start with electrostatic sensing and actuation principle. So we know that a parallel plate capacitor is one of the most fundamental arrangements that are used in sensors and actuators. So a capacitor can be broadly defined as two conductors that can hold opposite charge. So capacitors can be used either as a sensor or as an actuator. So if the distance or the relative position between the two conductors changes as a result of the applied stimulus, then the value of capacitance would change. So this forms the basis of capacitive or electrostatic sensing. On the other hand, suppose if a voltage or electric field is applied across the two conductors, then an electrostatic force would develop between these two objects. This is defined as electrostatic actuation. So electrostatic forces are most commonly used for micro actuation because of the fact that micro devices have a very large surface area to volume ratio and their mass is really small. This figure shows an electrostatically driven micromotor that is used as a MEMS actuator. So it consists of a rotor which is attached to the substrate with a hub and a set of fixed electrodes on the periphery known as the stator electrodes. The stators are grouped together such that each group of 4 electrodes are given biasing simultaneously. Okay, so the electrodes biased at a particular stage are identified by the arrow marks. Okay, now when the electrodes are given biasing, what happens is that an in-plane electric field is going to develop between the given stator electrode in the group with the closest rotor tooth next to it. So once this electric field develops, this is going to generate an electrostatic attractive force that is going to cause this rotor tooth to align with the stator electrode. That can be seen in the next figure. Okay, so this results in an angular movement of the rotor. Now in the next step, the electric bias is shifted to the next group of 4 electrodes, okay, resulting in a small angular movement in the same direction. Now we will look at the advantages of electrostatic sensing and actuation. The first one is simplicity. Electrostatic sensing and actuation are easy to implement because it requires only two conducting surfaces. No special functioning materials are required as in the case of piezoelectric or piezoresistive sensing. The second advantage is low power. Electrostatic actuation relies on differential voltage rather than current. So it is considered to be energy efficient for low frequency applications. At high frequencies, there will be a displacement current I of t which will develop in response to the bias voltage V of t. So this displacement current has a magnitude I of t is equal to C dV of t by dt. And the power delivered to the capacitor can be expressed as P of t is equal to I of t times V of t. The third advantage is the fast response. So electrostatic sensing and actuation offers a very high dynamic response speed. This is because the transition speed depends upon the charging and discharging time constants, and these are generally small for good conductors. So for example, the switching time of the mirrors that are present in a digital micromirror display array is very small, less than 21 microseconds, which means it is capable of supporting an 8-bit grayscale display. But there are also certain disadvantages associated with electrostatic sensing and actuation. One such disadvantage is the high voltage that is required for actuating operation. So high voltage is also going to introduce electronic complexity issues and material compatibility issues. This figure shows a parallel plate capacitor. So you have two conducting plates, each having an overlapping area of A, and let D represent the distance between the two plates. The dielectric constant or the permittivity of the media between the two plates is denoted by epsilon, where epsilon equals epsilon naught into epsilon r, where epsilon naught is the absolute permittivity and epsilon r is the relative permittivity. Now, the value of capacitance between the plates is defined as C is equal to Q by V, where Q is the amount of charge stored and V represents the electrostatic potential. The electric energy which is stored by the given capacitor is denoted as U, and U is defined as 1 by 2 CV square or 1 by 2 Q square by C. Now for a parallel plate capacitor, the electric field lines will be parallel to each other and perpendicular to the plate surface in the overlapped region, and there will also be the presence of fringe electric fields that reside outside the boundary of the electrode plates. Now according to the Gauss's law, the magnitude of the primary electric field E is related to the charge Q as E is equal to Q by epsilon A. The magnitude of the voltage is defined as the electric field times the distance d between the two plates. Therefore, the capacitance of a parallel plate capacitor can be defined as C is equal to Q by V, where V is nothing but E into D. So this can be also written as Q by Q D by epsilon A or epsilon A by D. So you can see that the capacitance of a parallel plate capacitor is proportional to the permittivity of the media between the two plates. It's directly proportional to the area of the two conducting plates and inversely proportional to D, where D represents the distance between the two plates. Now the capacitor can also be used as an actuator to generate force or displacement. So the magnitude of the force equals the gradient of the stored electric energy U with respect to the dimensional variable of interest. So F is defined as dou U by dou X or 1 by 2 dou C by dou X V square. Now if the plates are moving in a direction along their normal axis, then the gap between the electrodes will change. So you can define F as dou U by dou D or 1 by 2 epsilon A V square by D square. Now you know that C is equal to A epsilon by D, so you can rewrite this as 1 by 2 C V square by D. So by replacing the general dimensional coordinate as X, you can write F is equal to dou U by dou X or 1 by 2 dou C by dou X into V square. Now we will look at the thermal sensing and actuation principle. So most materials will undergo thermal expansion. That is, the dimension and volume of structures made up of semiconductors, metals and dielectric materials have a tendency to increase on rise in temperature. So the volumetric thermal expansion coefficient of a material is defined as alpha, which is equal to the relative change in volume delta V by V to the change in temperature delta T. The linear expansion coefficient of a material is the change of only one dimension of the object due to temperature variation. That is, beta is defined as delta L by L divided by delta T. The relation between the volumetric and linear expansion coefficient is given by the equation alpha is equal to 3 times beta. But in practical cases, you will see that the extent of expansion due to a temperature rise is very limited. So for example, if you consider a 1 millimeter long silicon cantilever beam, for a temperature rise of 100 degrees Celsius, it will elongate by only 0.26 micrometer. So even for thin film materials such as silicon nitride, polycrystalline silicon films, the thermal properties such as thermal expansion coefficient depends upon the exact composition of the material. Now actuators can also be designed based on the thermal expansion of liquid or air. So we know that for an ideal gas, the relation between volume and temperature is given by PV is equal to nRT, that is equal to nKT, where N represents the number of moles, R represents the universal gas constant, and T represents the absolute temperature. Capital N over here represents the number of molecules, K represents the Boltzmann constant. Now thermal sensors can be of three types: thermal bimorph sensors, thermal couples, and thermal resistive sensors. The first one is a thermal bimorph sensor. A bimorph element or a bimetallic strip is made by binding two materials having different values of thermal expansion coefficient. So here I'm considering this beam consists of two materials having a thermal expansion coefficient of alpha 1 and alpha 2, where alpha 1 is greater than alpha 2. On subjecting this bimetallic strip to a temperature rise, you can see that this bimorph element will undergo a mechanical displacement. So by measuring the amount of displacement, you can measure the variation in temperature. The second kind of thermal sensor is a thermocouple. A thermocouple is being made by two wires of dissimilar materials when they are joined together at one point. So this kind of arrangement constitutes a thermocouple. So it is used to measure the temperature difference between the joined sensing junction and the reference junction. So on applying a heat to the joined sensing junction, an open circuit voltage gets developed across the reference junction. So this open circuit voltage is linearly proportional to the difference of temperature. So the Seebeck coefficient alpha S is defined as the ratio of the open circuit voltage developed to the change in temperature. So here delta V is defined as alpha A minus alpha B times delta T, where alpha A and alpha B represent the Seebeck coefficient of the two materials which are used to form the thermocouple. Now as the size of the wire and beads reduces, the output of the thermocouple reduces. In order to overcome this drawback, we use a thermopile, which is formed by connecting a series of thermocouples in series. So here the output voltage of a thermopile can be written as delta V is equal to N times alpha A minus alpha B times delta T. N represents the number of thermocouples joined to form the thermopile. So here there are three couples used, so hence its delta V is 3 times alpha A minus alpha B into delta T. The next type of sensor is a thermal resistive sensor. So a thermal resistor is nothing but an electrical resistor that has a good amount of temperature sensitivity. So the resistance of a thermal resistor is related to the ambient temperature by the equation RT is equal to R0 into 1 plus alpha R T minus T0, where R0 is the resistance of the material at a temperature T0 and RT is the resistance at a temperature T. Here alpha R represents the temperature coefficient of resistance. The term thermistor is used when semiconducting materials are used to form the thermal resistor. Now we will look at a thermal actuator. Actuation in micro devices can be achieved by simply injecting or removing heat. So the change in temperature profile is going to result in a mechanical displacement or a force output. Now, a common example is the inkjet printers, which eject ink droplets based on the thermal expansion of the liquid ink. So this figure shows a schematic diagram of a single thermal inkjet printer nozzle. It consists of a micro machined fluid chamber with an opening, and there is a micro heater which is embedded on the substrate within the cavity, and when you apply a pulse of electric current, it is going to raise the temperature of the heater, and that is going to produce a vapor bubble. So this vapor bubble is going to squeeze the liquid ink and then eject a droplet. So upon cooling, the vapor bubble is going to collapse and the cavity will be refilled again for the next firing. So because we are using a microfabrication method, the volume of ink and the thermal mass associated with the ink is very small. And for commercial ink cartridges, it will take only 1 microsecond or less for this vapor bubble to get initiated, and approximately 15 microseconds for the ink to be ejected. So this table over here shows the characteristics of electrostatic actuation and thermal bimetallic actuation. So the advantages of electrostatic actuation is that it is capable of low power operation at low frequencies and it has a high response speed. The disadvantage is that the range of motion is relatively small and it requires a large area or footprint in order to generate large force and displacement. In the case of thermal bimetallic actuation, the advantages are a larger range of movement can be achieved and a smaller footprint is required for comparable displacement. But the drawbacks of thermal actuation is that you require moderate to high power operation as current is used to generate ohmic heating, and at the same time the response speed is lower because the time constant is depending on the factors of thermal heating and dissipation. Now we will look at sensing and actuation based on the piezoelectric effect. So the direct effect of piezoelectricity is when certain materials such as quartz can generate an electric charge or voltage when it is under a mechanical stress. The inverse effect is when the same material can produce a mechanical deformation or force when an electric field is applied to it. Now, this piezoelectric effect is commonly seen in an acoustic transducer, in microvalves, accelerometers, speakers, microphones, or even chemical sensors. Now, a piezoelectric crystal can be considered as a mass of minute crystallites or domains. Because of the random distribution of domains throughout the material, there will be no overall polarization or piezoelectric effect. So a crystal is being made piezoelectric in a chosen direction by means of Pauling. Pauling means exposing the material to a strong electric field at an elevated temperature. So under the action of this field, the domains will align with the field will grow at the expense of the others. That is, the material will lengthen in the direction of the field. When the field is removed, the dipoles will remain locked in a particular alignment, giving the crystal a polarization or a permanent deformation. Now, the crystal can be depolarized either by mechanical means or thermal means. So if the piezoelectric crystal is heated to a certain threshold temperature, the vibration may be strong enough that the domains will become disordered and the element becomes depolarized. So this critical temperature is called the Curie point or Curie temperature. So the safe operating point for a material is halfway between 0 and the Curie point. Now, in order to provide a strong piezoelectric effect, the piezoelectric material has to be poled in a particular direction. Although there are certain materials which exhibit a natural or spontaneous polarization. The direction of positive polarization is chosen to coincide with the z-axis for a rectangular system. So alternatively, the normal stress components along the x, y and z directions are denoted by the subscripts 1, 2 and 3 respectively. Similarly, the shear stress and strain components about these x, y and z axis is denoted by the subscripts 4, 5 and 6. In a piezoelectric crystal, the equation that relates electrical polarization D with the applied mechanical stress T is given by D is equal to small d into T plus epsilon into E, where small d represents the piezoelectric coefficient matrix, T represents the mechanical stress, epsilon represents the electrical permittivity, and E represents the electrical field. So you can see that the electrical polarization has two parts, one arising from the electrical biasing and the other one due to mechanical loading. So this is the general form of the constitution equation, where T1, T2, T3 represent the normal stress along the axis and T4, T5, T6 represents the shear stress components. Now in this equation, suppose if there is no electric field present, then this second term can be eliminated. Now the unit of the piezoelectric constant is the unit of the electrical displacement D divided by the unit of stress T. So D is epsilon into E, and the units of epsilon is farad per meter and the unit of E is volt per meter. So divided by T, the unit of stress is force per area, which is Newton per meter square. So in effect, you will get the unit of piezoelectric constant is Coulomb per Newton. Now the total strain can be related to the applied electric field by an inverse equation. S is equal to capital S T plus D into E, where capital S represents the compliance matrix, T is the stress applied, D is the piezoelectric coefficients, and E is the electric field. So if there is no mechanical stress applied, then this term can be neglected and your strain is related to the electric field vector. So if there is no mechanical stress present, then the strain S would be related to the electric field E as S is equal to D into E, where D represents the piezoelectric coefficients. Similarly, the electromechanical coupling coefficient K gives you a measure of how much energy is transferred from electrical to mechanical or vice versa. So K square is defined as the energy converted to the input energy. Now we will look at the concepts used in magnetic actuation. So a magnetic field can cause internal magnetic polarization for a piece of magnetic material. This phenomenon is known as magnetization. Now the magnetic field intensity is defined as the driving magnetic influence which is external to a magnetic material. So any piece of magnetic material will contain magnetic domains. So the strength of the internal magnetization depends upon the extent of ordering of these magnetic domains. The magnetic field density B is defined as the induced total magnetic field inside a piece of magnetic material. So the relationship between B and H is B is equal to mu naught into H plus M, where mu naught stands for the absolute permeability of the medium, H represents the magnetic field intensity, and M represents the internal magnetization. So this can also be written as mu naught into H plus chi into H, where chi represents the magnetic susceptibility of the medium. This is also equal to mu r mu naught into H. So a magnetic material which has a weak and positive magnetic susceptibility is called a paramagnetic material, and one which has a weak and negative magnetic susceptibility is known as a diamagnetic material. So for paramagnetic and diamagnetic materials, the relative permeability is very close to 1. For ferromagnetic materials such as iron, the values for relative permeability are very large. Now, what is the difference between hard magnets and soft magnets? A hard magnet is one that retains the magnetic polarization even under zero external magnetic driving fields, whereas a soft magnet is a ferromagnetic material that has a very low remanence and it will exhibit internal magnetization only when it is subjected to an external magnetic field. This figure shows the full magnetization curve for a ferromagnetic material. So you can see that the linear relationship between B and H is valid only for a certain range of H. Once the external induction field H reaches a certain level, then the magnetization will reach a saturation point that is known as saturation magnetization. This represents a situation when all the available domains within a piece of magnetic material have been aligned to one another. Now, on removal of the external field, that is when H becomes equal to 0, the ferromagnetic material will lose a portion of its magnetization. So the fraction of the saturation magnetization which is retained even after H is removed, this is known as remanence of the material or remanent magnetization. Now the measure of the reverse field needed to reduce the magnetization to 0 after having reached saturation is known as the coercivity. So coercivity is a measure of the field needed to drive the magnetization back to 0. The area enclosed by the hysteresis curve will indicate the amount of magnetic energy stored in a magnetic material. Now this figure shows the hysteresis curves for hard magnets and soft magnets. So you can see that for a hard magnet, a large fraction of the saturation field is being retained even when the external field is removed. So this is desirable for permanent magnets and magnetic recording or memory devices. So this shows the hysteresis curve for a soft magnet. So the narrow hysteresis loop shows that a small amount of dissipated energy is used for repeatedly reversing the magnetization. So this is desirable for transformer motor cores in order to reduce the energy dissipation with the alternating fields associated. Now we will look at certain selected principles of micromagnetic actuators. In a magnetic actuator, the magnetic field is used to produce force, torque, or displacement of the microstructures. So this driving magnetic field can act on a number of elements, including current carrying wires, inductor coils, or pieces of magnetic material. A Lorentz force actuator uses the interaction between a current carrying conductor and an external magnetic field. So the Lorentz force which is acting on a single moving charge Q is given by F is equal to Q into V cross T, where V represents the velocity of the charge. The magnitude of the force developed is given by F is equal to QVB sin theta, where theta represents the angle between the velocity and the magnetic field. The direction of the resulting force can be determined using the right hand thumb rule. That is, if the thumb is pointed in the direction of the velocity of the positive charge and the fingers in the direction of the magnetic field, then the palm faces the direction of the force on the charge. The force will be perpendicular to the velocity of the charge as well as the magnetic field. Magnetic actuator can occur as a result of the interaction between a permanent magnet and an external DC magnetic field. A common example is the magnetic compass. So, the permanent magnet which is used in the magnetic compass is nothing but a hard ferromagnetic material. So, if the internal and external magnetic field lines, if they are aligned, then there will be no force or torque exerted on the compass needle. But the compass needle will experience a torque when the direction of the internal magnetization is not aligned with the local earth magnetic field lines. So that torque is going to cause the needle to rotate until the internal magnetic field lines is lined with the external field lines. So this principle of interaction can be extended to the microscale sensors and actuators. Now, irrespective of the method by which it is generated, the external magnetic field can be classified into two broad categories: a spatially uniform magnetic field and a non-uniform magnetic field with a gradient. So depending upon the type of magnet, whether it is hard or soft, and their initial orientation in the field, whether it is aligned or misaligned, the net force or torque can be produced. So this figure shows the interaction of the hard as well as soft magnetic pieces in two types of field, namely the uniform external magnetic field and the non-uniform external magnetic field. So the pieces 1 and 2 represent hard or permanent magnetic pieces, and the pieces 3 and 4 are soft magnets. So for pieces 1 and 3, their internal magnetization is parallel to the external magnetic field, and for pieces 2 and 4, they are intentionally misaligned. So in the first case, that is part A, there is no external magnetic bias applied. So the permanent magnets are already polarized, and since there is no external magnetic field, the soft magnets are not. So neither of the pieces will experience any net force or moment because of the lack of a magnetic driving force H. In the second case, a spatially uniform magnetic field is applied. So this magnetic field is going to polarize the soft magnetic pieces 3 and 4 so that they become magnetized. Now the internal magnetization is parallel to the external magnetic field lines for the pieces 1 and 3. So they will not experience any force or moment. But for the pieces 2 and 4, the internal magnetization is at an angle with the external field lines. So the pieces 2 and 4 will experience a net torque but no net force. In the third case, when a non-uniform magnetic field is present, what happens is that again the soft magnets get polarized and the internal magnetization is parallel to the external field lines for the pieces 1 and 3. So they will experience a net force. The pieces 1 and 3 will experience a net force, whereas for the pieces 2 and 4, the internal magnetization is at an angle to the external field lines. So these pieces 2 and 4 will experience both a net force as well as a torque. To conclude with, in this presentation, we discussed the working principles of sensors and actuators based on the electrostatic forces and thermal forces. We also discussed the working principle based on the piezoelectric effect and magnetic actuation principles. Thank you.